Okay, this video is about series. Some of the first k terms of a sequence is called the series, or you could call it the first n terms. That's often what I refer to it as. That just means if you add together a bunch of terms of the sequence, you call it a series. So for example, we might have the sequence 1, 3, 5, 7, 9. If you put plus signs between all of those and start calculating a sum, then we would call it a series instead. It can be written as capital S sub k or capital S sub n or whatever variable you're using to represent the term number. When you add together some terms in a sequence, it's called a partial sum. Partial because you're not adding together every term in the sequence, especially if it's infinite, but you're often asked to find the sum of the first 7 terms, for example, so that would be called a partial sum. So you might write that as S sub k equals A1 plus A2 plus dot dot dot. Of course, that dot 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 means A3, A4, A5, where that's, of course, the value of each term, all the way up to A sub k, which is whatever term you're trying to find the sum up until. So in this case, it would be A sub 7 if you were trying to find the sum of the first 7 terms. There's another notation for writing a series, and that's called sigma notation. That big Greek letter you're looking at is a capital sigma in Greek, and it's got something below it and something above it. Now, below it tells you which term number to start with, and above it tells you which term to end with. And it sometimes is written with different variables, so I wouldn't get hung up on these i's or k's or whatever. But there's going to be a number below and a number above. And the number below tells you which term to start with, the number above tells you which term to end with. And then what comes after the sigma is the formula for the sequence that you're dealing with. So I think it'll make more sense if you see an example of it. Actually, let me skip ahead to this one. So just so you can see what the sigma notation looks like, write out what is meant by, here's example A and example B. So as you can see in example A, they're using I. In example B, they're using R. So like I said, you might see different variables. Don't get hung up on that. Just notice what the number is of the term they want you to start with, which here is 1, and the term they want you to end with, which here is 5. So this means you're finding the sum of, that's the way we read sigma, the sum of the first 5 terms of this sequence, term 1, 2, 3, 4, and 5. So what that looks like written out for this sequence is to plug in 1, 2, 3, 4, and 5 wherever you see I. So here that's 1 to the 4th plus 2 to the 4th plus 3 to the 4th and so on. Notice the exponent is not changing because the exponent was 4 in the formula and should stay 4. It's the variable that changes. In the second example, the variable they're using is R. This time the variable is in the exponent and the base is constant. The base is 3. I want us to figure out the sum of the 3rd term up to the 7th term. So that would look like, scroll down here, plugging in 3, 4, 5, 6, and 7 wherever you see the variable, which is in the exponent. And here they're not asking you to evaluate it. They just wanted you to write it out so you could see what the notation was all about. I'll go back to the example that I skipped. I doubt you'll ever see anything quite this complicated. Let me pull up a screen shade here. So here's an example. For the sequence 1, 3, 5, 7, 9, find the sum of the 2nd through 5th terms. Now, this is such an easy sequence, and they're only asking you to find the sum of the 2nd through 5th terms. And if I got this on an exam, I would literally just take out my calculator and add, or my brain, the 2nd term plus the 3rd term plus the 4th term plus the 5th term. You can actually see them right here. It's 3 plus 5 plus 7 plus 9. And calculate what that should equal. If I do that real quick mentally, that's going to be 3 plus 5 is 8, plus 7 is 15, plus 9 is 24. Okay, so the answer that we're looking for is 24. Just so you can see how sigma notation is going to work. If you had to find the sum of the 2nd through, I don't know, 84th term or something like that, you might want a formula to deal with that. So here's the sequence. If we wrote an explicit definition for it, remember the explicit definition formula is this. We have to plug in the 1st term and the common difference. So I plug in the 1st term, which is 1, and the common difference, which is 2. It's an arithmetic sequence. And then I'm going to simplify that until it looks like this. Of course, we could test it, make sure we got the right formula. If I plug in 4, for example, this gives me 2 times 4 minus 1, which is 7. And sure enough, that is the 4th term. Okay, so now we have our explicit definition. Since it's asking us for a sum, we can write it in sigma notation like this. The sigma stands for the sum of, the number below is 2 and the number above is 5 because it asks us to find the sum of the 2nd through 5th terms. That means we're going to plug in the values 2, 3, 4, and 5 to the explicit formula and then just evaluate it. And sure enough, it comes out to 24. So sigma notation works if you have the sequence already spelled out for you. It's often easier just to add them together on your calculator. If you have a formula instead of the sequence written out, then it's easy enough to just plug right into the formula. So here is another example. I'll pull up a screen shade here as well. It's asking us to evaluate this sigma, or this sum of the sequence is 2 to the nth power, so they give it to us in a formula. And we're finding the 0 through 5th terms. That means we're plugging in 0, 1, 2, 3, 4, and 5. So that's going to look like this, because the variable is in the exponent here. And it actually wants us to evaluate it. So this time I have to figure out what each of those terms is and add them all together. So the sum I got here was 63. Here's a more complicated example of writing a sequence or a series in sigma notation. It's tricky because it's not arithmetic, so we can't just use that little formula to come up with the explicit definition. I doubt, again, that you'd get one this complicated, but it's not so hard. It's just not one of the arithmetic or geometric ones that we've dealt with before. What's interesting about this sequence is there is a pattern, but it's not adding the same thing every time, and it's not multiplying the same thing every time. Instead, it's helpful to think about it like this. So here's the sequence written out, a little bit bigger. If you think about this is being term 1, this is being term 2, and so on. I didn't continue that pattern, but you'll see that it works. This is term 1, and the top of the fraction is the number 1. This is term 2, and the top of the fraction is the number 2, and so on. The top of the fraction is always the term number. The bottom of the fraction, meanwhile, is the term number plus 1. The term number plus 1, the term number plus 1, and so on. So you can think about these as being n on top and n plus 1 on bottom, where n is the common. And then, of course, I changed the color so you could see it. The first term is positive, second term is negative, third term is positive, second term is negative, and so on. The hard part of this definition is to come up with how do you deal with that negative. And so what I came up with is a -1 needs to get put in front of each term, but sometimes we want that -1 to turn positive. Right, so every other time we want it to be a positive 1 and then a -1 on the next term. So I'm trying to come up with a consistent definition that works for every single term. That's what an explicit definition is. So as you can see, I did a little creative thinking, and I made the exponent on the -1 be n plus 1. And if you think about it, the first term is going to end up being raised to the second power, because 1 plus 1 is 2. And we know when we have a -1 raised to the second power that it is positive. Then the next one is going to be -1 raised to the third power, which will be a -1, and then it'll go back to being positive on the next term, and then back to negative on the term after that. So by putting these two pieces together, we can come up with this explicit definition. -1 to the n plus 1th power is the complicated way of dealing with the alternating sign, and then n over n plus 1, this part, is how you actually get those numbers, like the fractions, 1 over 2, 2 over 3, 3 over 4, and so on. And then the sigma just goes from 1 up to 99, because the last term that they ended with is 99 over 100, which would be the 99th term. So again, I doubt you'd come up with one that tricky on a test, but it's not so far beyond your scope of understanding that I wanted to skip it. So I wanted you to at least see it. Here's a couple of properties we need to understand about sigma notation, and this is going to matter more when we study calculus next year. But here's a sigma notation series, right, where the formula is just 5i. And if you actually spell it out, it's 5 times 1, 5 times 2, 5 times 3, 5 times 4, and 5 times 5, because it asks us to do the sum of the first through 5th terms. Now, because of the distributive property, we can just factor out that 5, put it in front, right? And then it's just the sum 1 plus 2 plus 3 plus 4 plus 5. So a cool property of sigma notation is shown here, that if you have a coefficient in your series, you can just pull it out and write it in front of the sigma, do the sigma of just 1 plus 2 plus 3 plus 4 plus 5, and then multiply your result by 5. So you're going to see this in more complicated examples in the calculus unit, but this is a little intro to that. And same thing here, another cool property of sigma notation, and you could do this out with numbers if you wanted to prove it, but it's not necessary at this point. But if you have the sum of multiple different functions, or like a polynomial that's split into different pieces like that, a term plus another term, you can separate it and do it as two separate sigmas, right? Two separate series. Now, this is the much more applicable part. So these next 3 slides are the much more applicable part for our exam. The type of things you're going to see. We're going to dive specifically into arithmetic series right here. And we're going to use this formula when we need to find the sum of, for example, the first 20 terms or the first 80 terms. This formula is pretty quick and pretty easy. It's in the formula booklet, but they also give you this other version of it. I'm just going to ignore that. It's easier to use the one that I circled in red. So here's how we're going to use it. Find the partial sum for the first 50 terms. This is the down and dirty application. This is what you're going to actually have to do. We're going to start with the formula I just showed you on the previous slide. Always start by writing your formula. And let's talk about what each of these pieces means. So n is, whatever term you're trying to find. Are you trying to find the sum of the first 50 terms? Then that's 50. The first 80 terms, that would be 80, and so on. A sub 1, we should know from our other formulas, is the first term. And A sub n is the ending term, right? It's the term, the 50th term, or the 80th term, or whatever the term value is of the last term that you're trying to add together. So here, 50 over 2. 3 is going to be our first term, and A sub 50 is the last term, but I don't know what A sub 50 is. Right here, I can only see the first 4 terms, and somehow I need to plug in the 50th term. Well, good thing we have a formula that we learned for how to evaluate for the 50th term, right? It's this formula that we learned for an arithmetic sequence. So if I want to find the 50th term, I'm just going to use that old formula. Plug in the pieces I know, right? First term, I'm trying to find the 50th term. The common difference of this sequence was 5. I did that just by looking at it. 3, 8, 13, 18. And I put that in a calculator. I got 248. So 248 is my final term of the series that I'm trying to calculate, or the partial sum that I'm trying to calculate. So I plug in all the pieces to the sum formula and then evaluate it on a calculator. So 6,275 is the sum of the first 50 terms of this sequence. So this is a really straightforward, simple application of partial sums or series. A slightly different take on it here. If we had to find the sum of this series, notice that instead of ending with a dot, 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 it ends with 81. That means that it's a finite series. So we're going to basically just find the sum of -3 up through 81. But we don't know how many terms come in between, right? So we need to figure out which term this is that the series is ending with so we can use the formula. So here's the series written a little bit bigger, ending with 81. And I want to figure out 81 is the which term. So this time I need to solve for n. I don't know which term it is, so I plug the 81 in for the value of the term. The first term of the sequence is -3. The common difference is 4, which means the only thing I don't know is which term is 81. So I solve this equation. I figure out that 22 is n when the value is 81. So it means 81 is actually the 22nd term of this sequence, right? This is the first, this is the second, this is the third, this is the fourth. There's a bunch in between, and it turns out that this is the 22nd term. So that's what we just determined, which is helpful because if I want to find the sum and I need to use this formula, now I can plug that 22, that n, right in here. It's the 22 over 2. And then, of course, I'm adding together the first term and the final term, and then I evaluate this on a calculator. This partial sum, or this sum of this whole sequence is 858. And that is all.